Hey everyone, Dr. Yu here. Today we're going to look at chemical reactions. I skipped a couple of lessons, and that's because I received a request to talk about chemical reactions first. So I'm going to go over this lesson today, and then I will go back, finish the other lessons. Here are the objectives from ATI. You need to be able to identify covalent and ionic bonds, which we touched on in the earlier lesson, but we'll go over that again because you may see an example of a chemical and then you need to be able to tell whether the chemical bond formed within that molecule is a covalent bond or ionic bond. Second, you need to identify simple chemical reactions. We'll cover a few types of chemical reactions, and again on TEAS, if there's a question on that, you may see an example of chemical reaction and then identify what type of chemical reaction it is. Next, you need to know how different factors may affect the rate of chemical reactions. We're going to look at pressure, temperature, concentration of substrates. Next, you need to know what enzymes are, what they do. Basically, they're biological catalysts for chemical reactions, right? They can greatly speed up the rate of chemical reactions. You will see some common basic molecules, and you need to know what they are. So I have a few examples here, and then we'll talk about them later. Last, it's about pH, acids and bases. So you need to know the basic information about acids and bases and their corresponding pH range. All right, let's look at chemical bonds first. You might remember a little bit about these two types of bonds. Ionic bond is formed by complete electron transfer. For example, let's say we have sodium chloride. We have sodium that will donate one electron to chlorine, and chlorine will accept that electron. And this way, both atoms fulfill the octet rule. So they both get 8 electrons in the valence shell, which is the outermost shell. So again, in ionic bond, there's an atom that completely loses an electron or donates an electron. And then the other atom will completely gain that electron. So this is about the valence shell that we talked about previously. If an atom has a lower number of electrons in the valence shell, they tend to lose the electrons, right? They tend to donate the electrons to another atom. But if atoms have higher number of electrons, like numbers that are very close to 8, then these atoms tend to gain electrons, right, to get to 8. So the atoms that have very few electrons in the valence shell, they will donate or lose electrons. They will become cations. Cations are positively charged ions. And atoms with a higher number of electrons, 5, 6, or 7 in the valence shell, they tend to gain electrons, or accept electrons to get to 8, right? So they will become anions, which are negatively charged ions. Okay, now usually ionic bond is formed between metals and nonmetals, and this is specifically stated in the ATI TEAS manual. So in order to identify whether a molecule has an ionic bond or not, you kind of need to know what metals are and what nonmetals are. So I found this color-coded periodic table from online, and this is very helpful because all the metal elements are in this light blue color. So you can see elements on the left are usually metals, and elements on the right, which is in red and this yellow color, they are nonmetals. So these are metals. They tend to lose electrons and become positively charged ions. And the elements on the right side, they're nonmetals. They tend to gain electrons and become negatively charged. So together, when you have a a metal atom and a non-metal atom, they tend to form ionic bond where there is complete electron transfer from metal atoms to non-metal atoms. Okay, next type of chemical bond is covalent bond. So the participating atoms share electrons. Right? There's no complete transfer. They share electrons. So think about roommates sharing apartments, right? They're sharing that space. And the same thing for atoms in atoms forming a covalent bond. They're sharing the electrons. So this type of bond is usually formed between two non-metal elements. And that's because if you look at ionic bond, metals on non-metals, they are very, very different in their electronegativity. You might know what this is, but just think of this as the power to pull electrons towards themselves, or think of this, the power to attract electrons. All right. So metals do not have a very strong electronegativity, but non-metals do, especially elements with a very high electronegativity, for example, chlorine, fluorine. So when that happens, non-metals with a high electronegativity tend to completely take the electrons away from the metals, right? So this forms ionic bond because there's complete lose and gain of electrons. But when you look at non-metal elements, they are not very different in electronegativity. So this means when they interact chemically and form a bond, nobody is very strong, right, to attract electrons. They have a similar power to attract electrons. And as a result, they will more or less share electrons, and that will form a covalent bond. Now, these chemicals, they have a covalent bond. For instance, in water, hydrogen and oxygen are sharing electrons. If you look at water molecule, oxygen has 6 electrons, and that's not 8, right? It's missing 2. So what do? You will have hydrogen come in and 2 hydrogen atoms, right? H2O. So there are 2 hydrogen atoms, and each hydrogen atom will share its only electron. So you can see for oxygen, this is good, right? There's 1, 2, 3, 4, 5, 6, 7, 8 electrons, so that satisfies the octet rule. And for hydrogen, it has only 1 electron shell, right? So which can only hold up to 2 electrons. So if you can get up to 2, then you're good. If you look at each hydrogen, let me use a different color. There are 2 electrons, right? So again, that satisfies the octet rule. So everybody's happy and water is energetically stable. Okay, so here are just more diagrams explaining the formation of ionic bond and covalent bond. So we talk about sodium chloride, and you can see sodium completely loses this electron to chlorine, right? So sodium will get down to the next shell, which has 8 electrons. And for chlorine, which has 7 electrons in the valence shell, it gains this 1 from sodium. So now it has 8, right? So everybody's happy. The sodium chloride molecule is stable. And we also looked at water. Okay. Now I want to mention that in covalent bond, you can further have a polar covalent bond and a non-polar covalent bond. The TEAS study manual does mention polar and non-polar covalent bond, although this is a little bit in depth, and I don't know how likely they're going to have a question on polar and non-polar covalent bond on the test. My guess is it's not very likely. So you can put this on the low priority list, but just in case, let's see what they're about. What is polar covalent bond with this non-polar covalent bond. Now, when you look at water, so this is water, and you can see this is oxygen. Oxygen has 8 protons, which means oxygen has 8 electrons, right? 2 in the innermost shell and 6 in the next shell, which I drew earlier. And then we talk about hydrogen has only 1 electron, so it's going to share that electron with oxygen. So for hydrogen, there's 2. For oxygen, there's 8 in the valence shell. So everybody's happy. Water is stable. All right. Now, when you look at the oxygen atom and the hydrogen atom, you will notice that oxygen atom is a lot bigger than hydrogen atom. So oxygen has more protons in the nucleus, which are positively charged, right? And we know that opposite charges attract. So oxygen with more positive charge in the nucleus can pull or can attract the electrons much, much better than hydrogen. So you think of oxygen as a bully, right? Very strong bully, strong in terms of attracting electrons. So when oxygen and hydrogen, 2 hydrogen atoms form a water molecule, the electrons are not shared equally. Electrons not, this is the key word, not shared equally, because oxygen atom is much, much stronger in pulling the electrons closer to its nucleus, right? And this is what basically electronegativity is about. Oxygen has a higher electronegativity. So the electrons, even though they're shared, are going to be closer to oxygen. And this is going to lead to an unequal situation where oxygen, let me use a different color, is going to be slightly negative over here. And that's because the electrons, which carry negative charge, are closer to oxygen. So that makes oxygen atom slightly negative. And because the electrons are further away from hydrogen, right? So in relative, hydrogen atoms are going to be slightly positive. So you can see over here, slightly positive, slightly positive. So for each water molecule, this creates a negative end, which is the oxygen end, and a positive end, which is the hydrogen end. So there are 2 poles, right? Think about the Earth. There's a North Pole, there's a South Pole, they're the opposite, and the same thing for water molecules. A negative end, negative pole, and there's a positive and a positive pole. So water is polar. So when electrons are not shared equally, this is going to create a slightly positive end and a slightly negative end. And that's going to lead to a polar covalent bond. Chemicals with a polar covalent bond are normally hydrophilic. Hydrophilic. Because of the uneven distribution of the electric charge, it makes the chemical usually very water soluble, because water itself is polar, right? So it likes to interact with other polar molecules. So if a chemical, for example, hydrogen chloride, which also has a polar covalent bond, dissolves in water very easily. Now I'm going to give you an example of a non-polar covalent bond. Okay. Think about oxygen gas, which is formed by a non-polar covalent bond between the 2 oxygen atoms. So we talk about there's 6, right? 6, 6. So for each oxygen atom, there's 6 electrons in the valence shell. It needs 2. But when you have 2 oxygen atoms, then they can share electrons. Each oxygen atom will share 2 electrons with the neighboring oxygen atom. So you can see they are sharing these 2 and these 2 electrons. So now when you look at each oxygen atom, you will notice that. Now now for each oxygen atom, there's a 1, 2, 3, 4, 5, 6, 7, 8. So now you get to the 8 electron in the valence shell, which is the stable configuration. Look at the other oxygen atom, same thing, right? Now there's 8 electrons. But you have 2 oxygen atoms sharing the electrons. And of course, because they're the same atom, they're going to be equal in their electronegativity, right? They have exactly the same strength in pulling the electrons. So the electrons are going to be shared equally. In this case, electrons are shared equally. And this is going to create a non-polar covalent bond, which means there is no negative and no positive end. Electrons are distributed evenly within this molecule. So non-polar molecules are usually hydrophobic. So they do not dissolve in water very easily. Now, this might not be a very good example because we're looking at a gas molecule. I will give you another example, and that's fatty acid. Remember, we talk about fatty acids when we talk about lipids, and the fatty acids have long chains of just carbon and hydrogen, right? Okay, I don't have enough space, but I just want to show you that you may have this long chain of, carbon and hydrogen, So carbon and hydrogen, even though carbon has 6 electrons and hydrogen only has 1 electron, these 2 atoms are very, very similar in their electron negativity. So carbon and the hydrogen are very, very similar in their electron negativity. So when you have a chemical bond formed between a carbon and a hydrogen atom, they are going to share the electrons equally. Share electrons equally. And when atoms share electrons equally, this is going to form a non-polar covalent bond, right? And we said chemicals with non-polar covalent bond are not very water soluble. And we know that fatty acids and other lipids are not water soluble, right? Because they are non-polar. So they're very hydrophobic. They do not like to interact with water. Okay, so that's everything about ionic bond and covalent bond. Next, we're going to look at different types of chemical reactions. ATIT's menu mentions 5 types of chemical reactions: synthesis, decomposition, single replacement, double replacement, and combustion. First, synthesis reaction. So this is pretty easy to understand. You are making a bigger molecule out of smaller atoms or molecules, right? So you are combining 2 things and make them into a new substance. For instance, sodium reacts with chlorine, and that will generate sodium chloride. But you probably noticed that this chemical reaction is not balanced, right? You have 2 chlorine atoms at the beginning of the chemical reaction. So in the end, you should have 2 chlorine atoms. And if you put 2 in front of sodium chloride, that means you should have 2 sodium atoms at the beginning of the chemical reaction. So this is the correct chemical reaction after balancing everything. There are 2 terms I need to mention real quick: reactant and product. From these chemical reactions, you probably noticed that the arrow indicates the direction of the reaction, right? So the reaction is going from left to right. The substances on the left side are going to be the reactant, right? The substances that go into the chemical reaction, and they will react with one another and it generates product. So the substances on the right side of the chemical equation is going to be the product. All right, so that's synthesis. Now, decomposition is almost the opposite, right? You are breaking down a molecule or a compound into simpler elements, right, that makes up this compound. So A, B can break down into A and B. So that's a decomposition reaction. I have an example here. Let's say we have carbonic acid, H2CO3, that can break down into carbon dioxide and water. So that's an example of decomposition reaction. The third type is single replacement reaction. So in this type of chemical reaction, an atom or group of atoms is replaced by another. You can see in AB, this reactant B is replaced by C, the second reactant, right? So in the end, you have AC and then B, the component by itself. So that's a single replacement reaction. A quick example here, iron can react with copper sulfate, and iron is going to replace copper in copper sulfate. So we get iron sulfate and copper. So that's an example of a single replacement, right? Only copper in copper sulfate is replaced. All right, now double replacement reaction. This is where you have two replacements happen at the same time. Okay, so you can see AB and CD, then B and C are going to switch. So you end up with AC and BD. A quick example here, sodium hydroxide can react with copper sulfate, and this is going to generate sodium sulfate and copper hydroxide. Right, so you can see basically, let me use a different color. Sodium and copper, these are switched, right? So two replacements happen, right? So you have sodium hydroxide that gets replaced and also copper sulfate that gets replaced. The last type of chemical reaction is combustion. This is where a substance reacts with oxygen. Normally the substance reacts with oxygen. And the reaction is exergonic or exothermic, meaning the chemical reaction releases energy, usually in the form of light and heat. A good example that everybody is very familiar with is wood burning, right? When you go camping, you burn firewood, and that's burning of the organic matter. Usually it's a carbon compound, reacts with oxygen. And that releases light and heat, right? This is when you burn wood, it really keeps you warm. I have another example here. This is a burning of a methane gas. CH4 is methane. So methane is combustible, can burn at the presence of oxygen, and this chemical reaction generates carbon dioxide and water. This chemical reaction tells you that methane is a greenhouse gas, right? Because when it burns, it releases carbon dioxide. And in fact, methane is one of the most potent greenhouse gases in the environment. And I have a quick note. I know I put in the comment that TEAS is unlikely to ask you to balance chemical reactions, but it is mentioned in the TEAS study manual that the number of the same element should be the same on both sides of the chemical reaction. So if you start with a one oxygen molecule, which is two oxygen atoms, in the end of the chemical reaction, you should have, two oxygen atoms. Could be in different forms, but you should have two oxygen atoms in the end. So this is pretty much balancing chemical reactions, but since it's not listed in the objectives, I think it's less likely that you will be asked to balance chemical reactions. But it's still good to know this rule and to know that the number of the same elements or atoms should be the same on both sides of the chemical reaction. I did see a question from the study manual. It says, predicted the outcome of this composition reaction. So the correct answer is going to be in terms of factors affecting chemical reactions, the common ones are temperature, pressure. Those are the physical factors that can either speed up or slow down chemical reactions. Now, normally higher temperature will increase the rate of chemical reaction. That's the most common case. And I've seen a question from the study manual that asks you about, different factors. The correct answer is temperature generally, higher temperature generally increases the rate of chemical reactions. So they assume that this is a, general situation. Higher temperature can energize atoms so that the atoms are moving faster. They are more likely to collide when the chemical reactions happen, right? So that's the reason. Now, there are some cases where if the chemical reactions release heat, exothermic reactions or exergonic reactions, then the higher temperature may decrease the rate of chemical reactions. Pressure. Now, again, in general, higher pressure increases the rate of chemical reactions. And the reason is very similar with increasing temperature. Higher pressure will push the atoms and molecules closer, right? Again, this will increase the chances of collisions, which lead to chemical reactions. Catalysts, whether it's chemical catalysts or biological catalysts, which are basically enzymes, will increase the rate of chemical reactions. And the reason is that these catalysts can lower the energy of activation required for the chemical reaction to start. If you have a startup company, you need the initial funding to get the company started, right? And same thing for chemical reactions. So you need a little bit of energy to get the chemical reaction started, and then the chemical reaction can proceed, right? So catalysts can lower the amount of energy of activation. So it's easier for the chemical reactions to get started and then proceed. Lastly, concentrations of reactants and substrates. The higher the concentrations are, the faster the chemical reactions will go, right? Because you have more molecules available for the chemical reactions to happen. And in terms of enzymes, the reactants, we'll talk about reactants, right? Those are the chemicals that are usually on the left side of chemical reaction. The reactants are going to be the substrate for enzymes. So the more substrates you have, the more raw material enzymes have to work with, right? So this will also increase the rate of chemical reaction. Catalysts, we already talked about this. Those chemicals can speed up chemical reactions, right? And then the science behind it is that these catalysts can lower the activation energy, the energy required to get the chemical reaction started. Now, this is important. A lot of people get this wrong. During a chemical reaction, catalysts are not changed. So they're still the same molecule, and they're not used up during the reaction. And so whether, how many chemical reactions have completed, the amount of catalysts will be the same, will remain the same. And they can be reused over and over. So whenever a catalyst chemical molecule completes that chemical reaction, it can be reused again. It will just go find another substrate and start a chemical reaction. Okay? So catalysts are not changed or destroyed in chemical reactions. They can be used over and over. Enzymes are biological catalysts. We have actually talked pretty extensively of some enzymes in the A&P section. We talk about amylase, which can digest starch. We talk about trypsin, which digests proteins, right? Now, I have a list of common molecules mentioned by the study manual, so you can look through and make sure you know what they are. Ionic compounds, you can see that they all have a metal component, right? Usually ionic bond is formed between a metal and a non-metal. So sodium, potassium, calcium, they're all metals, form ionic compounds. Next, covalent compounds. covalent compounds, usually the covalent bond is formed between non-metal elements, right? So we already know water, carbon dioxide, oxygen, glucose. Make sure you know what glucose is, and ethanol. So ethanol is commonly known as alcohol, right? And you can definitely burn alcohol. So ethanol can react with oxygen and burn, and that will be combustion reaction. Acids and bases. I don't see very hard questions on acids and bases on TEAS. So I think the most basic thing you absolutely have to remember is the pH range for acids, which is lower than 7, right? If you draw the pH scale, I have a diagram showing the scale here, but I'm just going to draw again from here. So you have 0 to 14, 7 is neutral. Between 0 to 7, that's going to be acids. Between 7 to 16, that's going to be bases. Acids are chemicals that can donate hydrogen ion or accept hydroxide ion. It's the same thing, right? If acids can donate hydrogen ion, then hydrogen ion can react with hydroxide ion and takes away the hydroxide ion. So that's what acids do. And the bases, they donate hydroxide ion or they can accept hydrogen ion. Interesting fact, when you eat sour stuff, fruits, orange juice, you can taste that sourness, right? And that's because of the presence of hydrogen ion released by those acidic substances. The hydrogen ion can interact with your taste buds, which contain chemical sensors that will send signals to your brain when they come into contact with hydrogen ion. And then your brain will interpret that signal as a taste of sourness. That's pretty interesting, right? Hopefully this can help you remember that acids are substances that donate hydrogen ion. So when they dissolve in water, they will release hydrogen ion into the solution. All right, now buffers can absorb excess hydrogen ion, and this will prevent the pH from decreasing, right? Keep pH from decreasing. Buffers can also absorb excess hydroxide ions, right? And this will keep pH from increasing. The more hydroxide ion you have, the more basic or alkali the substance is, right? Because you are going this way. For acid, you're going the other way. So if buffers can absorb hydroxide ion, that will keep pH from increasing. Right? If buffers can absorb excess hydrogen ion, then that's going to keep the pH from decreasing, right? From getting more acidic. So buffers are chemicals that can resist pH change. That's why they're called buffers, right? They provide a buffer for any pH fluctuations. And a very common buffer ion in our body that keeps pH more or less stable is bicarbonate ion. Okay, now let's look at the practice problems. Number 1, which of the following phase is an example? Oh, I have a typo here. Which of the following chemical is an example of covalent bond? Lithium, copper, calcium, they're all metals, right? So if you have metals forming a chemical bond with the non-metals, chlorine, sulfate, nitrate, those are non-metals. So they are going to form ionic bond. So the correct answer for covalent bond, which is non-ionic, is going to be C. Both hydrogen and chlorine are non-metals. So when they form a chemical bond, it's going to be a covalent bond. And it's going to be a polar covalent bond because chlorine is a lot more stronger than hydrogen in attracting electrons. So the electrons tend to stay closer to chlorine atom. So the chlorine end is going to be slightly negative, and the hydrogen end is going to be slightly positive. So hydrogen chloride is a polar molecule. Number 2, in this chemical reaction shown here, what type of chemical reaction this example demonstrates? So zinc reacts with copper chloride, which generates zinc chloride and copper. So which one is it? Now, the only component that gets replaced is over here, right? So basically zinc replaces copper and form zinc chloride. So that's going to be a single replacement. If I have another example, this might not be a real chemical reaction, but I just want to show you an example. If I have a zinc, let's say nitrate, react with a copper chloride, and then you get zinc chloride and copper nitrate, that's going to be a double replacement. Number 3, alkaline substances such as sodium chloride and potassium chloride are often used in soap making process. Which of the following is the pH level of these substances? Alkaline basically means basic, right? So these substances are basic, meaning they donate hydroxide ions, right? And then they have a pH higher than 7. So the correct answer is above 7. All right, we're done with this lesson. Good job, guys.